In last week's modules, we developed an EV frontier for two assets. In this module, we're going to expand the framework so that we can look at multiple assets. So we can look at 4, 5, 6, 100, conceivably, in a portfolio framework. The framework that we're using is called the Markowitz portfolio model. Markowitz, whose picture you see here, developed this framework. Littner developed this framework at about the same time, but this is just a general way of finding the frontier, or the Markowitz frontier of risky assets. Markowitz's major observation, and for that matter Littner as well, is that diversification can lead to a portfolio, a set of assets that are held that will maximize or give the highest expected level of return for a given level of risk. So think of it this way: you're selecting a risk level, you find the portfolio or the weights that you put in each one of these assets that gives you the highest expected return. This is called the Markowitz efficient portfolio. And you can think here, for each level of risk you will find a different portfolio that has a different expected return, and actually as you lower the risk you will lower the expected return. The problem of finding that portfolio, we'll go over the math here in the following slides, and we'll put it in the framework of an Excel spreadsheet. You can solve for Markowitz efficient portfolios in an Excel spreadsheet, as we'll illustrate here. When we are doing this, we will actually reverse the problem a bit. Rather than finding the highest expected return for a given level of risk, we will set a return level and then minimize risk. Same observation is given on this overhead, but we will, because it's easier to do, find a minimum level of risk for an expected return level. An example of how this works is given on this slide. The graph here, which shows risk or standard deviation on the horizontal axis, expected return on the vertical axis, and then the middle of this is a list of, or an area, and you see that brown area, and that's bounded by that curve 1, 2, 3. The brown area is where all the assets lie. So you'll see assets lying in here at different points, and what we are going to do is combine those into portfolios by picking a risk level, finding the highest expected return, or alternatively picking an expected return and finding the lowest risk level. And what you'll find is that line segment, or the curve from 2 to 3, where you see the highlight box now. That is the set of risk efficient portfolios. These are a set, and there's a whole lot of them, of portfolios on that line segment from 2 to 3. These assets, or these portfolios and the assets that are in them, give the highest return for a given level of risk. And what we're going to do is find that curve given a set of assets. To set up this math problem, we are going to have to use some notation. You see this listed here. This notation refers to each of the assets in the portfolio. We have n assets in that portfolio. N equals the number of assets. Each one of those assets has an expected return. You see that denoted there by the expected E to the RI. So each one of the n assets has an expected return. They also have a variance. Variance is given by VAR to that, the variance of that asset. We can state that alternatively as the standard deviation. So each of the assets has an expected return, a variance or standard deviation, and that's describes totally the returns of that asset. We're assuming that those distributions are normal, so we're not allowing skewedness or kurtosis or anything of that nature. The last set of notation we have is the correlation between assets I and J, and there will be a number of those. If we have three assets, there will be two correlation coefficients, and that will grow as we have the number of assets increase. The final notation is the weight of asset I in portfolio. We're going to restrict that weight to be between 0 and 1. 0 means that there's no assets invested for asset I. There's no funds for asset I. A 1 would mean that all of those items are invested in that asset. Given our definitions of expected returns, standard deviations or variances, correlation coefficients, as well as our weights, we can determine or describe the returns from our portfolio in terms of the returns and the variance. And this portfolio is a combination of assets. The expected return, you can see in the highlighted box, is from our portfolio, where we invest WI in each one of the assets. The expected return is actually the weighted average, where the weight is the proportion invested in that asset. So it's a weighted average of all the expected returns from each one of the assets. You see there in that highlighted box the two asset case, which is what we used last week. It's weight 1 times expected return 1 minus weight 1 times the expected return of asset 2. Our variance, which you now see in the highlight box, is given by the formula that you see listed there. This is a statistical relationship. You should probably memorize it or put it on your memory sheet or cheat sheet. The variance of a portfolio is the sum of the weights squared of each of the variances plus the cross terms. Weight I, weight J times the standard deviation of I times the standard deviation of J times the correlation between I and J, asset I and J. Notice that asset I and J goes down, that correlation goes down, though that term will go down. If it becomes negative, it would actually subtract. You see in the asset case, or in that highlight box, the two asset case, which we used last week. Just go back to our formula and you'll see it. And note that the correlation coefficients also have to range from -1 and 1. Let me describe this mathematical optimization problem now that we've defined the returns and standard deviation from our portfolio. In referring to this optimization problem, I'm going to use the equation numbers to the right-hand side of the screen. You see four sets of equations, 1, 2, 3, and 4. Equation 1 gives our objective function, which is to minimize the variance. That minimized variance is exactly the same definition as from the previous slide. We want to minimize that variance, subject to the constraints that you see listed there, 2, 3, and 4. Our first constraint, which is equation 2, is that our returns from our portfolio, which is on the right-hand side of the equation there, has to be greater than or equal to a constant. What we're going to do is vary that constant, and for each level of that constant, minimize this problem and find the weights that minimize our objective function. So here, equation 2 is just the definition of the expected return for the portfolio. We're going to set a constant and we're going to minimize our variance. We're also going to do that subject to the constraint that all of these returns have to equal 1. The sum of our portfolio weights have to equal 1. We have to invest all our money into our portfolio. And the final constraint there is that each of the weights has to be greater than 0. We have to, or greater than or equal to 0. Actually there's one constraint for each one of our assets. So this is the math programming problem that we're going to solve. We're going to set that up in Excel now. I'm going to give an example in Excel using these means and these standard deviations for 4 assets. So we're going to do a 4 asset model, asset 1, 2, 3, and 4. You see the mean standard deviations listed there, and the last set of numbers is the correlation coefficients between these 4 assets. So these are our assets that we're going to be using in our mean variance Markowitz portfolio model and solving for it. Here in the end is what we are going to solve with our portfolio problem. We are going to develop that black line there, that EV frontier, which is the black line that goes through asset 1 or starts at asset 1 and goes down to our left and down. That's our EV frontier. That EV frontier is composed of the 4 assets that you see listed there, asset 1, 2, 3, and 4. And again, what we're going to do is use our Microsoft Excel program to solve for this EV frontier that you see listed there. Couple points here, which you'll also see listed on the next slide before beginning our EV frontier derivation. Our EV frontier will begin with the asset with the highest return. Asset 1 has the highest return. We cannot get a higher return than that asset. There's no mathematical way of combining assets to get a higher return than that. What we will do to find our EV frontier is just systematically lower our constant in our equation 2 in the previous slide, or 2 slides ago. We'll systematically lower our expected return from 0.128 in this case to 0.12 to 0.115, and you can pick any number that you want and just keep going down. Eventually you will find that you can no longer get lower standard deviations, in which you've come to the end. You'll note here in this case that doesn't necessarily go through asset 3. Here is the spreadsheet that we're going to use to solve for our Markowitz portfolios. Let me describe the setup here. Here you see, and again, everything in yellow is something you enter. Here's the weights for asset 1, asset 2, asset 3, asset 4. Right now, asset 3 has all the weight. We enter the expected returns for each one of the assets and the standard deviations. We also calculate the variation, which is the square of the standard deviation. We also enter the the correlation coefficients. You see them listed here. This EV table can solve up to 5 assets. It is given in the EV solutions for this week's modules. So pull that up, and again, weights here for each one of the assets, expected return, standard deviation, correlation. Now I want to show you the portfolio values here, and that's given on this line here. First, the portfolio weights, they always have to equal 1, or you can change those. You could put 0.2 in here, then the portfolio would have 1.2, but that would mean there's more funds than invested. 1. Our expected returns here. This is our portfolio's expected returns. That's that equation on that equation. You can see it's just the weight of each one of the expected returns. And then we have the calculation of the variance. And the variance here is the standard deviation is the square root of the variance. So that's the square root of the variance. And I'm going to show you next the calculation of the variance. The variance calculation is given over to the right. Let me just scroll on over here. Here's the calculation of the variance, and it's given by this block here. If you look at the equation, you will note that what we're doing here is giving weight 1, weight 2, weight 3, weight 4, weight 1, weight 2, weight 3, weight 4, the standard deviation, and then we're just cross multiplying things in here, but also by the correlation coefficient. You can look at the formula and look at this equation here. Here's our calculation of each element in that formula, and then we sum it up here. Look at the equation, look at the calculations, and they come out to be the same. Actually, the variance in most portfolio problems is calculated using matrix notation, and this is very easy to implement in matrix notation, but you see the calculation of the variance there. And just go look at it, and you'll see that those two are calculated the same. The final item to note down here is our benchmark return, or a constant, and that's given right here, and we're going to vary that. This is equation 2 in our setup. This is equation 1, our variance. Here's equation 2. Our equation 3 is this portfolio, and each one of these weights must be greater than 0. So those are our equations that we will have to use for this math programming problem. We are going to use Solver to come up with this math programming problem. And I'm going to describe the solver in the next slide. But if you go into your data sheet, you should see solver listed here. If you do not, go into File, Options, and Add-ins. And you'll see here that I have the active application add-ins, the solver add-in here. If you don't see that, your solver add-in is listed down here. Click on it and add it so that it's an active application add-in. Now we're going to set up the solver problem. Again, if you're on the data sheet, you should see solver here in the analysis toolbox or analysis bar. If you don't see that, come over to File, Options, Add-ins, and solver add-in should be an active application. If it isn't, go down here and make sure it is an active application. We're going to go into solver now and set this up. And we're going to use the equation 1, 2, 3, 4. I'm going to do it in that exact order. Start with solver. I want to set an objective, and what I want to do is, remember, I want to take my variance and I want to minimize it. I'm going to minimize that variance by changing the weights. The weights are in C6 through C10. And now I'm going to add my constraints. I want my portfolio, or excuse me, my expected returns to be greater than or equal to my benchmark returns. Okay. Then I'm going to, so there's my first equation. Expected returns has to be greater than my benchmark returns. I also want my weights to sum to 1. Portfolio weights. So I'm going to add that constraint. This one has to equal 1. Got that equation. Weights in the portfolio have to equal 1. Now, the weight of each of my asset has to be greater than 0. Greater than or equal to 0. First asset has to be greater than or equal to 0. If you just say greater than, all the assets will have a weight, but some of them will be very small. There's my first weight. I could do this faster, but I'm just going to continue. Add third. has to be greater than or equal to 0. Okay. Add this one. Has to be greater than or equal to 0. And then the fifth one, just to be complete, oops, I'm sorry, add. Fifth one has to be greater than or equal to 0 as well. Alright, I've set it up. Now I can solve it. And let me just hit solve. And I want to keep my solution here. I'm going to describe the solution to this on the next slide. We've set up our solver. Now I'm going to solve it for certain specific problems. Alright, remember I said the highest expected return we could get was our highest return on our asset, which in this case is 12.6. Let's just put that right here, 12.6, and solve it. Oops, I gotta hit 0. No. Solve it. I'm going to find the portfolio that results in a 12.6 return and the minimum variance for that, which you already know. I want to keep my solver solution. Okay. Now I have this solved. For a 12.6% return, I put all my weight in asset 1. Surprise, surprise, surprise. And my standard deviation, or my variance, which will go together, up and down together, is the standard deviation of that asset. Again, there's nothing magic here. Let me write a little formula here. What I want to do here is sketch out the EV frontier right here. And I'm going to start with 12.6. Actually, I've done this already. Let me put this in black. I'm just collecting here 12.6, my standard deviation of my portfolio, and then each one of the weights. I'm going to copy that down here. I've already copied that, but just to do this, let's say I'm going to copy this, copy it down here, just paste values. Alright, I've got my first portfolio. The next slide is going to show you how to do the second portfolio in our EV frontier. Now I want to use Solver to sketch out the rest of my portfolio, or excuse me, my EV frontier, and all the portfolios that are on my EV frontier. The way I'm going to do that is to systematically lower this benchmark return, and I'm going to do it in 0.5% increments. And I'm going to go from 12.6 to 12, then I'll go 11.5, 11, 10.5, and just sketch out the portfolio. Let me do 12. Now I'm going to solve it. Make sure it's pointed at the right cells. Solve it. Alright, so now I solved for my 12 portfolio. And that portfolio, has 0.85 weight on asset 1 and 0.15 weight on asset 2. Or excuse me, asset 4. So to get my 12% return, I combine those two portfolios into, or two assets into a portfolio. And let's just copy this result down. Actually, I've done that already. So for a 12% return, I have a 0.103 standard deviation, and my weights are, let me do this, shown there. Now let's do a 0.115. Do a solver again. Solve. And now I have 0.73 weight, 0.28 weight. And I can keep doing that as we move down the assets. and I'll show you that on the next slide. Alright, I've solved this for the following cases, and you should have this, or if you get the spreadsheet you'll have this, from 0.126, 0.12, 0.15, 0.11 expected return, the minimum standard deviation, amount invested in asset 1. Sort of interesting, you always have something invested in asset 1. Asset 2 comes in for a while, asset 3 comes in, asset 4 comes in. Alright, I want to show you something, and we've sketched out the EV frontier here. I'm going to graph this. Let me copy this over here, and I want to graph this. And I'm just going to copy some things around. This is my standard deviation now. I just sort of changed the axis around. I did that because I can use the insert function. Highlight this, and I'm going to insert a XY graph. And I'm going to connect the dots. Well, let's make it smooth. Alright. Here's the EV frontier. I want you, and this would be this point here, right there where I'm pointing at right now, would be this point right here with asset 1 having all the weight. As you move down this curve, you get different weights of the assets. Now look here, it's a straight line. You, as an individual, would never choose to invest in any point on this line right here. Because all you're doing is you're not getting any lower standard deviation. You might as well go up here and get your highest return for your standard deviation. Look, the standard deviation's remaining the same here. And there's the highest, and it might be somewhere between those points. So you would be up here. Now note, at that point, we're investing in asset 1, asset 3, and asset 4. Almost never, and I never say never, would the lowest return be just an investment in a single asset. It's also sort of interesting, just for your background. Look at this. This is our lowest returned asset. It happens to include asset 1, asset 3, and asset 4. Asset 1 and asset 4 are some of our more risky assets. So even our portfolio that's our least risk includes some of our assets with the most variance. Just shows you the power of putting portfolios together. Some points here. We've used Excel to sketch numerically our EV frontier. Our EV frontier always begins at the highest return or has its highest return, begins there too, at the highest return asset. You can never go above that. You can change the standard deviation or the risk, but you can't change the highest return. You can sketch out the frontier by solving for different expected return levels, and you'll eventually reach the lowest standard deviation. And we illustrated that all in that problem.